today, Dario Benedetti from Paris. He will speak about old and new conformal field theories at large N.
Yep. Okay, thank you. Yeah, first of all, I would like to thank Raimar and Johannes for this nice workshop and the invitation. Since I had only some old research about new conformal field theories, I thought I would try to say something new about old conformal field theories. But we'll see. It's actually preliminary stuff, so I will just give you a glimpse. So first of all, I will give you some introduction and some background material just to put everyone same footing. And then I will, so the old thing is the ON model, and it's one over an expansion. The new CFTs are the tensor, like ON cube field theories. And but first start with some motivation. So so one of the idea is to use these two tools of quantum field theory, which are very powerful, which are the renormalization group, which is has a crucial role in our modern understanding of quantum field theory, as it singles out special theories, which are the fixed points of the renormalization group. And in principle, we think of quantum field theories, all other quantum field theories, as deformations of fixed points by relevant perturbations. And now fixed points, interacting fixed points are hard to study. So one needs typically non-perturbative tools. Some are provided by the functional RG that you heard about, but most of the time, say the thing which is most under control is perturbation theory, but it becomes hard to apply to interactive fixed points. Now, usually the scale invariance of fixed points is enhanced to conformal invariance. This is not a theorem, but typically it's the case. It is a theorem in this special case in 2 dimensions. Then if you have conformal invariance, you can apply different strategy, which is like the bootstrap strategy. And you basically assume the conformal invariance and you impose consistency relations to try to constrain the data of your theory. And this has led to many interesting results. But so far, also it's limitations, like mostly it's limited to unitary theories at 0 temperature. And you might ask, why do you want non-unitary theories work for statistical physics? The unitarity is not really a necessary thing. And there are many interesting models which don't translate into a unitary theory in the Minkowskian. And also the link to the path integral origin of the model is often unclear, because you're just trying to abstractly work with some correlators without knowing where they come from. So it would be nice to kind of link more these two approaches. And one way to do that, actually, we'll argue, is provided by the large N methods. And large N methods definitely provide you with computable toy models in the strict large N limit. And the idea is, if you include 1 over N corrections, you can ideally also approach finite and more realistic models. And they can allow you to show interesting things, like that the renormalization group actually also some models admits an interactive fixed point, that such fixed point is a CFT, and you can mix RG and CFT methods, which is what was my motivation here. So large N limits have a long history, and but typically there are 2 limits that have been considered a lot. One for the ON model, it's essentially a vector model. You have a field with one index, which transforms under the n group. And when you take n large, Feynman diagrams that dominate are cactus diagrams. So for example, for a two-point function, something like this, for a theory with quartic interactions. And interesting, they lead to the strict limit to easily solvable Schwinger-Dyson equations, which basically reduce just to mass gap, because here there is no momentum circulating in this loop. So it's just, these are just mass renormalization. Somewhat it's too simple. And on the other hand, you have matrix models where you have typically two indices. For example, some fields transforming the adjoint of UN. And that was shown by Toft like 50 years ago. The large n limit in this case is dominated by planar diagrams. And this plays an important role for many situations. And but unless you have specific things like supersymmetry or special properties we heard in the Grosse-Buchener model, typically these models are still too complicated. If you have a quantum field theory and want to sum all the planar diagrams, it's a difficult task above 0 dimensions. So there are two ways that I want to discuss in this talk to go in between the too difficult and too simple. And one is just take still the vector models, which I said were a bit too simple, but you go to higher orders in the 1 over n expansion. Well, soon it becomes very complicated. In fact, the most advanced results, I think they are also from like 40 years ago. But I will try to discuss what we are trying to do with a student polytechnic. And the other approach is to look for tensor models. It's, as I told you, the two cases where vectors, matrices, the natural thing is to add one more index or more. And in this case, it was shown that the dominant diagrams are melonic diagrams. Melonic diagrams are something like this for a vacuum diagram with two vertices. And you can iteratively insert kind of the open melon where you open here one edge. So you get like a sunshine diagram, which you can repeatedly insert as many times as you want. These are melon diagrams. And the things I will present are work in collaboration with Razvan, Sabine, David, and Kenta. So first, some background, just quickly. So just a reminder, what is the CFT in one slide? Essentially, the idea is you impose invariance of endpoint functions, and say we are in d-dimensional space. You impose the invariance under SOD plus 1, 1 if you are in Euclidean signature, or SOD, 2 if you are Lorentzian. And this restricts very much the correlators. So in particular, two-point functions of primary operators are completely determined by their scaling dimensions, which are the eigenvalues of the dilation operator, the scaling operator, and the spin, so which is the irreducible representations of the rotation subgroup SOD here. And for example, for scalars, so I have 0 spin, and I take two scalars with dimension delta I, delta j, the correlator is orthogonal. So if the dimension of these two operators is different, then the correlator is 0. And if it's equal, then it's 1 over x I minus xj to twice the dimension of the operator. All local operators are either primaries, which have this kind of correlators, or descendants, which are derivatives of primaries. Then you move on to n equals 3, the 3-point functions. These have, again, are completely fixed up to a constant this time. I mean, in principle, you could have a constant also here, but you just normalize your operators. So you fix it to 1. After you fix that, you cannot rescale the operators anymore. So you have a constant here, which you cannot remove, and some function dependent on the distances within the 3 points. this constant appears also in the OP coefficient, which is what allows you to reduce all higher endpoint functions to this data, the 2 and 3 point function, because every time you have an operator OI and OJ in an endpoint function, here I omit the other spectator fields, you can use the operator product expansion, which reduces this to a sum of one single operator plus its descendants. And so you go from an n-point function to an n-1 point function. And so you can iteratively do this. And here this works very well because this OP depends only on these coefficients from the 3-point function and the scaling dimension. And it is a convergent expansion for CFTs. So that's very powerful. Now, on a different note, I have just now let's consider just there I was just talking about correlators, so that's where CFT can be more abstract. I don't need to talk about path integral or anything. Well, suppose instead we take the usual approach of quantizing a Feynman and take a path integral and I have an action. And so on. So I typically introduce sources for the field. For the field. Now I want to, and this I assume you are familiar with, but I want to recall briefly another slight generalization of that, which is to include the sources for bilocal composite operators. This goes under the name of Twobi formalism. So the idea is this: you take a partition function z, actually it's logarithm. Here you have a Gaussian measure with covariance c and an interaction part of the action. And instead of having just phi x jx, you have phi x jxy phi y. So the source j couples to this bilocal thing. And now, if you do the Legendre transform of this object respect to j, you define in this way an effective action, which now it's not the usual one with the local sources. So one PI, one particularly reducible effective action. This gives you a two particularly reducible effective action, which has the following structure. So there is a free theory part where you would obtain if you didn't have this S interaction here. It just has to depends on the covariance of the free theory, and this G is the argument of the effective action, so it's a free variable. And then there is a part which depends on the interactions, and it's the sum, well, minus the sum of all the two particularly reducible diagrams, meaning diagrams that cannot be disconnected by cutting two edges, constructed from the vertices of this interaction, and with G, this free variable as propagator. So here you don't really have to evaluate any Feynman diagrams because the diagrams are just an abstract way to construct things which are depends on G. Only when you evaluate G to some specific choices, you will have actually to perform the integrals. And how you get there? This comes from two key equations. So actually from the first one, it's a way to fix G. So this is the field equations of this effective action are the Schwinger-Dyson equation for the two-point function, meaning that the gamma dg equals 0, you rewrite it in this form, is G minus 1 equals C minus 1. This, I remind you, was the free covariance of the free propagator, the inverse free propagator, minus sigma, which is the self-energy. And now the self-energy is written, is the minus twice the derivative of this gamma 2 here, this piece here, respect to G. So it's a function of G. And so this is, in a sense, it's a closed equation for G. And as usual, as the usual interpretation, now if I invert this, I get a geometric series in sigma. And in principle, if you can solve this for G, then you plug this back into the thing, and you have usual Feynman diagram. So of course, this you cannot solve. I mean, first of all, the sigma comes from a sum of diagrams with this G, so you only you typically will include only a finite number of them, and then you can solve this perturbatively in the usual way. So you recover usual perturbation theory. But this is not how I want to use it, and that's because I wouldn't gain much from this formalism. So in principle, I will show you that in the large n limit, this thing will truncate, so I will have closed equations for G that I can actually solve more interestingly. The other equation, which is very similar in some way to this, is the next step. You take, instead of the first derivative, the second. Now, if you're familiar with that, in the usual 1pi effective action, if you take the second variation of the effective action with respect to the field, you get the inverse of the 2-point function. In this case, if you take the second variation of the effective action with respect to G, you get the inverse of a 4-point function, essentially. So to say this is a full 4-point function, to which I subtract this disconnected contribution and this contribution, which here depends on full 3-point functions, and it propagates one intermediate line. So the one particle irreducible contribution in this line. So essentially, this whole thing is a 4-point function, which is one particle irreducible in this direction. I cannot disconnect this object by cutting from 1, 2 to 3, 4, say from left to right by cutting only one line. And so this, then by construction, it has to have always at least 2 lines going from left to right. And so this I can write it as a geometric series in some kernel, which itself instead is 2 particle irreducible. So these gray boxes cannot be disconnected from left to right by cutting 2 horizontal lines. See? And so this geometric series, actually, you can show that I mean, it means that this object, which is, you can show that it's the inverse of the Hessian of gamma. So it can be written as a geometric series in this kernel, which then we define is called K. I mean, it's called the Bethe-Salpeter kernel, and typically it's denoted K. And essentially, it's the second variation of this gamma 2, which appeared again very shortly here. So this is another interesting object, and it's interesting, particularly now when you combine the two formalism, the conformal field theory and this 2pi formalism. So how do you combine them? First, you suppose that the Schwinger-Dyson equation has a conformal solution, meaning I have a solution that G of x and y has this form, and that higher endpoint functions also are conformal. Then it follows that the Bethe-Salpeter kernel can be diagonalized by conformal 3-point functions in the sense, in this particular sense, where I view the 4-point kernel as a kernel from from 2 variable to 2 variable, let's say. So I integrate over x3 and x4 with some function that depends on x3 and x4 and another variable z. And this function has precisely the form of a conformal 3-point function. Just by symmetry arguments, you can show that it follows that this thing, this integral, has to be conformal in x1, x2, and z. So by conformal invariance, it has itself the form of a 3-point function, because conformal invariance completely constrains things. So this has to be proportional to this, and the proportionality is the eigenvalue k of h and j. Well, then there is maybe some detail that, I mean, these things then here I'm using is phi x, phi r, and considering scalars as fundamental fields. And the third operators, the formula you have to insert has a certain dimension h and spin j. So and it was shown in the 70s that actually this 3-point function form a complete basis if the dimension h is in the principal series of the S of d plus 1, 1 group. So meaning that the h is d half plus imaginary part. Then using this basis, you can represent now the inverse of the Hessian of gamma. So you have to sum over the basis elements, which I said are labeled by the spin j. labeled by the spin j, by the dimension h, which is on the half plus imaginary. And here you have the basis elements, the eigenfunctions. So you have one and its conjugate. And so essentially here, this rho is a measure factor that comes out from this from normalization stuff. It's called the Plancherel measure, because this whole thing has also some group theoretical, well, obviously has a group theoretical interpretation. So what is model dependent is this part here, which was the eigenvalue of the Bethe-Salpeter kernel. So you have this 1 over 1 minus k. And well, actually, you can, this I told you was a complete basis for positive imaginary part, but by symmetries of this thing, you can show you can extend it to the whole imaginary line, vertical line. And you can, this integral over z can be reduced to a certain function, which is given dimensions are known. Now, so the situation is this: you have this integral over this vertical blue line, and what typically happens is that if you move it to the right, you'll find poles of this function, and so you can transform this integral into a sum by picking up the residues at these poles. And now these poles are, for the free theory, are just poles of this rho, so because in the free theory you have no k. And when you go to the interacting theory, typically what happens is that k has the same poles as rho, so actually those poles of rho don't matter because you have infinite of infinite. I mean, the limit is finite of this ratio. What matters is the poles of this denominator, which is 1 minus k. So the solutions of k equal 1 give you these poles. And once you do this just complex analysis thing of transforming this contour into a sum of residues, you find an expression of this type, which is precisely the OP expansion for the 4-point function. You take first two fields at x1 and x2, do the OPE, you take the other two fields at x3 and x4, you do the OPE, and so you get sum over 2-point functions, which are exactly can be exactly evaluated, and you have an expression of this type, where these are the OPE coefficient square, and this is known as conformal blocks. So this is something which is known, and the interesting thing is that if you can evaluate this k of h somehow, which is, I will argue, you can in the large n limit typically, then extracting the conformal dimensions that appear in the OPE spectrum, it just amounts to solving this equation, k equal 1.
I have a question. The number of poles, is it finite or is it infinite?
Infinite.
Okay. And you can reconstruct the whole function by summing over all residues?
Yes. Yeah, so it has been, so I mentioned before, so in fact, from this point of view, we understand, because actually it's been proved that the OPE expansion is convergent in conformal field theories.
So, but there's,
if these x1 and x2 are in a ball which doesn't include x3 and x4, let's for example.
But there's an accumulation point at infinity where the poles accumulate or something like that. Is there no problem with resumming all the residues?
No, I would say
okay,
no.
Good.
So, okay, so this is also background material. In principle, as I would say, this is for ordinary field theories. If you take just one scalar, phi4, is not very useful, this stuff, because you don't have good control on all these equations that I was showing here. I mean, except perturbation theory, but then you're back to perturbation theory. But so now I want to show you that in the large n limit, these equations become very nice. So first shot, that is an ON model. So I take the ON model, it's just defined by usually this partition function. I have again a Gaussian measure on fields phi, which actually are, I have n fields. I didn't write to say phi should have an index A, and when I write phi square, is actually sum over A from 1 to n of phi A, phi A. And so this is a Gaussian measure, and the interaction take quartic interaction with some mass term and the interaction. Now, it would be interesting to consider a more general class of models than maybe typical for high energy physicists, which is where I take this the dimension of the field phi. Sorry, it should be d half, not toward d half minus z instead of d half minus 1. So d half minus 1 would be the typical dimension, and that's I would refer to that as short range model. But in statistical physics and mathematical physics, it's also common to consider this other range where zeta is smaller than 1, and call this long range models. And the restriction to smaller than 1 is such that the short range kinetic term doesn't become relevant in this case. And also you have reflection positivity. And the restriction will be low. The lower bound is due to keeping this quartic term relevant. So if zeta becomes smaller than d over 4, then phi 4 becomes irrelevant, and then you have just mean field theory. So this is the bound. And now here I wrote a usual generating function with the local source, and that is useful for generating endpoint functions of phi and for studying spontaneous symmetry breaking of the ON model. But this will not be what I want to do. But first, let me also introduce a standard trick, which is the kind of intermediate field or Haber-Stratonovich. One rewrites the effective, the e to the minus s interaction in terms of an auxiliary field lambda with propagator 2, intermediate field sigma with propagator 2 lambda delta of x minus y. And with this interaction term, now we couple sigma with phi square. Now one could, because phi now it becomes Gaussian, one could integrate out phi and arrive at a formulation with only sigma, and where n is parameter, and you can view the large and limit as a saddle point approximation. However, in that way, you lose a bit of some information, or it becomes more complicated to retrieve certain information. So actually, I'll keep this mixed representation. So I have now a path integral, which has a Gaussian measure with covariance C over phi. There's this ultra-local covariance 2 lambda times the delta function over sigma, and this interaction between sigma and phi square. And now, instead of introducing the source, the usual local source, which breaks ON invariance, I only allow sources that respect ON invariance. So it means I can introduce a source for sigma, I can introduce a bilocal source for sigma, and a bilocal source for phi. So here's phi A at x, phi A at y. And so I have 3 sources, and I can now do a triple Lagrange transform and obtain the 2pi effective action, which takes this form. It depends on some fields S, D, and G, which are conjugate to these sources J, K, and L. And so the first part here is essentially the action for sigma rewritten in terms of at phi equals 0 and rewritten for S instead of sigma. So this was coming from the Gaussian part here, which I didn't write explicitly. This comes from this term here. And the phi term is not there because I didn't put a source for phi, so I don't see a mean field phi. I'm assuming the 1 point function of phi is 0. And then I have terms that generalize what I had written before for the general case. So there are some terms which are there would be there for the free theory if there wasn't this term. And then there is a gamma 2, which includes all the 2pi diagrams coming from this sigma phi square vertex. And now it comes a nice thing, because this I wrote everything, all these sources without indices. You see, I contracted directly phi A to have an invariant. And so all the powers of n are very explicit. And it becomes easy to do the 1 over n expansion for this for the diagrams that appear in this gamma 2. At lowest order, I draw them here. So the first is order n to the 0, so order 1. And it's this diagram where, sorry, I didn't write, but the solid lines will be the phi propagators, which are now this free variable g. So I have a g here and a g here. And the wiggly line is the sigma propagator, which I call d. So here there is a d and 2g. And the order 1 over n, I have these other diagrams with the crossing of d propagators and this one. And then so on. But you see that each order in 1 over n, actually I get a finite number of diagrams, which if I was to do the 2pi effective action just for phi, so without this sigma terms, I would have an infinite series already at this order here. So it is a convenient way to repackage the 1 over expansion of the ON model already. And I can look at the fields equation now. There I have 3 of them that derive with respect to sigma, d, and g. And if I and they take this form essentially. For S is actually quite simple because S doesn't enter here, so all the dependence on S is explicit. So I have the full equation for S. It takes this form, and in fact, if I tune lambda 2, there must be minus lambda gxx. Then I have the solution S equals 0. And then I will do that. So actually I will choose S equals 0. And so what you have to look is just this red part. So I have for the inverse propagator of sigma, still the delta function plus things that come from the 2pi diagrams. And for G inverse, I have C inverse plus the stuff that comes from the 2pi diagrams. And notice that this one has a 1 over n, and this one doesn't. This came from the fact that you have n phi fields, which gives you here an n trace log of G inverse, while you have only one sigma field, so there is no n in front of this term. So when you work out, yes.
What's the combinatorial properties of your graph that you put in your package? Have you characterize it or?
Finite n.
Yes, I mean, let's say pair 1 over n, you have a finite number of contributions, right? Do you have a characterization of tools?
Well, there is a usual characterization if you think of the phi loop as a vertex. You have this essentially the kind of in the loop vertex expansion. I mean, you have a fixed number of loops in from this point of view. You see, this is one solid line is a vertex, and this one, well, if you draw it outside a wiggly line, you will see that it's one loop. This one, if you draw them outside and shrink the solid line, you see it's a 2 loop. This one was also a 2 loop. So at order 1 over n to the k, you have k plus 1 loop from this point of view. But here I don't take all the loops diagram from this representation. I only take those which are 2pi, both with respect to the solid line and the wiggly line. So it reduces a lot. Yes.
So what's the relevance of fixing this relation of lambda 2 and lambda? Are there just parameters?
Yes, well, those are bare parameters. And so I tune lambda 2 to stay massless, essentially. So because the expectation value of sigma essentially is the mass of phi. I'll give you a mass for phi. And then, so I'm essentially tuning to the massless model because I want to go to the conformal limit. So first thing I tune to massless. It's not the whole mass thing. In fact, these diagrams might generate other mass. I might have to include other counter terms that I didn't write here, but to keep things simple, keep it like this. A leading order in Legend, this is all, but yeah. At higher orders, I might have to subtract other things to stay massless. So now I have this equation here. And so if I have first order, so I have this diagram. So if I derive with respect to D, which is the wiggly line, means I open this guy. If I derive with respect to to G, means I derive with respect to the solid line, and I open this or this. So the diagrams I get are these ones. plus order 1 over n. So this is the usual bubble diagram. And so now in this leading order means I take the strict large n limit, consistent solution of the Schwinger-Dyson equation. Now I will be obtained in the lambda to infinity or p to 0. What do I mean here? If I take lambda to infinity, I drop this guy. And in fact, you can see this is equivalent to tuning the model to the fixed point. Because this is a bare parameter at this order, tuning the renormalized dimensionless coupling to the fixed point is equivalent to sending the bare dimensionful lambda to infinity. But another point of view is just if you go to momentum space, here you have p to some power, and this is just 1 in momentum space. So as you go to p0, am I saying the other way around? Well, forget about that. It's a usual story, but it's, perhaps I got confused and I'm a bit late. But the main part is, forget is lambda to infinity is a fixed point anyway. So I drop that term and I have a scaling solution that solves this equation. You just plug the scaling ansatz for G here and for D and G here. You plug them here and you have a way to, I mean, actually for this one, because the 1 over n, this one, your first order, you don't take it. So you find that G is just given by C. And D inverse, when you drop this term, is just given by this bubble. So D is the inverse of this bubble, and you find that it has this behavior. So you find, okay, the leading order, as I said at the beginning, is very simple. The G has no anomalous dimension, it's the canonical dimension. Sigma instead has this dimension to zeta, which is the only non-trivial part of the large n limit here. And for the beta-salpeter kernel, also is very trivial at this order. There is actually vanishing eigenvalues, and so you find classical dimensions. So you find the OPE spectrum is given by operators of this type with 2 phi's and j derivatives within them. So this kind of composite operators here. And they are, the dimension is that's the canonical one is twice the dimension of phi because you have 2 fields phi, and plus j because you have j derivatives. So it's 2 delta plus j is the dimension, and you find this. This comes from this I wrote some time ago. This from this Plancherel measure here. So you have no k in this case, and so the poles just come from this row, and they happen to be precisely at this free theory values here. The only non-trivial thing is for j equals 0, where you don't have phi square as a composite operator, but which is because its dimension is below the half, so you don't pick it up when you move the contour to the right, where you pick up the you have only the sigma pole. So in a sense, sigma replaces phi square. This is all well-known stuff from a long time ago. So, but the non-trivial thing is to go to the higher orders. So if you start using usual perturbation theory, it gets a mess very quickly, and the higher orders become very complicated. So how did people do a long time ago? So they kind of use a self-consistent method that so for example, next to leading order, you keep order 1 over n term in the Schwinger-Dyson equation of G, which was this one with this term here. So this kind of rainbow diagram here, and then you plug in again a conformal ansatz for G and D, and try to solve things consistently. So it's not you are starting from the free theory and you do an expansion and you plug in an ansatz and solve consistently. So this will lead to equations for this amplitudes A and B and for this eta. And so there are actually 2 cases. The short range case, which you actually require positive eta here. So sorry, eta 1 is the first term in the expansion of eta in 1 over n. And when eta is positive, then you'll find a bit the argument I was trying to say before, but I foresee that you can discard the C-1 term by matching powers when you go to the IR. And because you have p squared essentially for C inverse and p to the 2 minus eta for the other terms. And so for p that goes to 0, you can discard the p squared. And you find then by using that, I mean, you can invert explicitly given these answers G, you just get some coefficients which depends on this on the dimension delta, which was d minus here written here. And then you get the Schwinger-Dyson equation reduces to these two equations, p delta plus a squared b over n equals 0, and 2p delta sigma plus a squared b equals 0. So these are two equations now for two variables, a squared b and eta, which is hidden inside these guys. So by solving these two equations, you can determine eta 1, the first order term in eta, and this combination is square b. And for the long-range model, things are a bit easier because actually there is no wave function normalization. You don't need eta, so you can keep it 0. And that means you keep C minus 1, and you only compute essentially the scaling function. Now, for going to the beta-Salpeter diagonalization, now the beta-Salpeter kernel again from the same diagram, but now I derive twice. So I open two legs. I had the diagram with 3 legs, and which I wrote here. This one I open on 2 legs. I can open this 2 or this 2, let's say, and I have so these various options that form this matrix. I cannot derive twice respect to D because there was only one propagator D, so here I get 0. But here, when I derive twice respect to G, or in the mixed ones. And notice on the first line, there is a 1 over n factor, which was again from the different scalings in the effective action. Now, the eigenfunctions of this K, again, are linear combination of 3-point functions, now with phi phi O and sigma sigma O. And the eigenvalues are ratios of gamma functions, which I don't write explicitly here, but, and they have poles at these values, which are, again, the classical values for this bilinear operators in phi or in sigma. But we don't want the poles of the eigenvalues, as I showed you to argue before. We want when the eigenvalues is equal 1. But it matters the poles because if I have an equation where I want to equate something, I want 1 equals 1. Oh, it's wet. 1 equal 1 over n, some function of h. And so I want this function of h to blow up with n as I. Okay, thank you. I will. Okay. So I just want to say that. So the poles are important because in order to get this equation to be satisfied, I need to get close to the singularity here, so that for n that goes to 0, this thing blows up, and so I have the small corrections to these dimensions, and this can compute explicitly. And some of these were known, some are new, but there are always some ratios of gamma functions, and I don't show them. Well, I didn't have time to include. But the important I want to show is the method, not the results, which are some ratios of gamma functions, which is not particularly important. So this, and the idea is this can be pushed to a higher order. It becomes, again, quite complicated, but it is one way to go. So the rest of the thing, which I'm doing 5 minutes, then was the tensor model. So, but you heard a bit, and most of you heard already several times. So I thought maybe I spend some more time on the new, on old stuff, which I'm trying to revisit. So instead, the new old thing is so the idea is instead of ON model, you look at ON cubes. It means you have n, for example, n cube fields. You label with 3 indices that go from 1 to n, and they assume that they transform each under an independent ON transformation. You get a new class of models in which you have more invariance because you have n cube fields, but O, and you don't have O of n cube invariance. You have O of n all to the cube. So it's much smaller than this. So it restricts less and you have more invariants. And these invariants are usually represented by graphical notation, but where each vertex represents a tensor with 3 indices and so on. But some people know, so for the others, it's going to be too fast. But the important thing is that there is still one master, and there are 3 quartic terms. There are 3 5-4 invariants now. And these models have been shown, well, in this precise case of O(n) cube by Carrozza and Tanas in 2015, that they have 1 over n expansion labeled by this degree that Joseph mentioned before. And the dominant diagrams, okay, when you forget about this structure, I mean, the representation is useful for combinatorial point of view, but in the end, when you want to do Feynman diagrams, I just view, as usual, phi4 as a vertex with 4 legs. So and this is what I get. So here, these are just the end result of the larger analysis that for vacuum diagrams, you get things like this. Is the melons I discussed at the beginning. And because you have 3 types of invariants, there is actually 1 invariant that gives you the melon, and the other 2 invariants can give you tadpole insertion, so a bit like in the vector model. So you have a mixture of these 2 types of diagrams at the fundamental level that you can iterate within itself. And this model has some, the melonic limit provides you, again, interesting things, but kind of repetition a bit of what I said before. So you get closed Schwinger-Dyson equation for the 2-point function. You get Bethe-Salpeter kernel obtained from few 2-pi diagrams. In this case, you have one more thing, which is you have 3, as I say, three coupling for the quartic invariants. There is one of them, which is called tetrahedron, which has no radiative correction. So things, let me show. So if you, moreover, you choose a long-range propagator, as I say, so as I introduced before, with this zeta smaller than 1. As I told you before, also you don't have wave function normalization. So you don't have wave function normalization in this case, and you don't have radiative correction for the tetrahedron coupling. So it means that that coupling is exactly marginal, and you will have a tunable parameter in your theory. And so what happens again, you have, as I said, I have a closed equation for the Schwinger-Dyson equation, which now includes this melonic diagram of sunshine in this case, which can be solved exactly in the long range case with zeta tuned to be exactly d/4. And the Schwinger-Dyson equation is essentially you plug in this ansatz for G, and the Schwinger-Dyson equation reduces to an algebraic equation for this coefficient zeta, which is solved by the generating function of 4 Catalan numbers. So essentially, the zeta are the sums of these melonic insertions, which have finite amplitude. So it's very nice, and you have also finite radius of convergence, which means that these melons proliferate and blow up, etc. Similar story for the 4-point function. You have the Bethe-Salpeter kernel, which is given just by these diagrams, and this one is an interesting one based on, again, on this tetrahedron coupling, because it gives you, once you iterate this geometric series in the Hit kernel. In the Bethe-Salpeter kernel, you get ladder diagrams. So, in fact, for the normalization of these 4-point couplings, what matters is all diagrams of this type. You can write the full beta function at all orders say there is 3 coupling. 2 of them, I call them G1 and G2, and they have a beta function which is quadratic in these couplings with coefficients which are function of this exactly marginal tetrahedron coupling, and are given by this kind of ladder diagrams with 1 extra vertex or with 2 extra vertexes at the end. So you can find then the exact solution and the critical exponents, and Well, I should maybe just mention this thing. When this gets real fixed point, a real critical exponents, when you choose this marginal coupling to be purely imaginary, which makes sense because this coupling is not bounded from below. So it's a little bit like doing phi cube theory. So we have a like for the Young model. So we have an imaginary coupling, but with this in the large N, we find all critical exponents to be real, OP coefficients to be real. So in fact, we can apply CFT methods as I illustrated more slowly before. Again, you look for the solution of K = 1, and you find the spectrum of operators with their anomalous dimensions, etc. Well, skip the other results. So, okay, just to conclude, I wanted to say that, okay, the large N limit is a powerful method for studying interactive CFTs. And as was known, the large N limit of the N model is very simple, but it gets a richer structure, which still, I think, much has to be done because the most advanced subleading orders in 1/n, because the most advanced results, as I say, are from 40 years ago, and I believe something can be done more. And we have some preliminary results in this step, but still ongoing work. For the Meloni case, instead, the rich structure already comes to the leading order. You have much more rich behavior already at the strict large N limit. And so we have a bunch of results, which I flashed very quickly through. So yeah, more work has to be done, I think. And of course, also for the tensor models in the 1/n expansion, there is still, it gets much more complicated even than for the ON models. So there is a lot of things to do there. And with that, I conclude. Sorry for being so fast at the end.